Hello everyone, I am Dr. Balaji Bhanu. This video content contains the number systems and how they are used as a coding for a digital electronic gadgets like a calculator and a computer. The contents of a short duration are counting in a decimal and a binary, what is the positional value, decimal to binary and binary to decimal conversion. The next coding is the BCD code and how these two are done with the help of electronic translators, the encoders and decoders. The other two codings are the number systems, hexadecimal and the octal number systems. The very first one is counting a decimal and a binary. As from the childhood, we are very familiar with a decimal number system. So, what is a number system is the number symbols what we are using for the representation of any data. In a decimal number system, we are using a 10 symbol, that is from 0, 1, 2 up to 9. So, totally the number of numbers in this system are 10. That is why the base is 10, which is also called as radix. Whereas, in a binary system, the symbols are only 2, that is 0 and 1. Therefore, the base is 2. Now, I will show you how to convert a decimal to a binary. We are doing by means of dividing with the number 2 successively. For example, you take a number 13. We are dividing with the number 2. There is what we get is a remainder 1 with a quotient 6. This is what the procedure of division with the number 2. So, 6 times, that is 12, and the remainder is 1. You separately write the remainder. Next, you take number 6 and divide with the number 2 once again. So, the remainder is 0. Write the remainder separately. Then, the next remaining digit is a number 3. So, you take that number 3 and divide with the number 2, and the remainder becomes 1, write separately. And again take number 1 and divide with the number 2. We cannot divide, therefore, you write 0 and remainder is 1. That means you are writing this number as it is. And finally, what you are doing is you are writing all these numbers from bottom to top. That means 1, 1, 0, 1. Therefore, finally, the decimal number in a 13 is equal to, the answer is 1101 with a base 2. How we are converting a decimal to binary. It is a small test for you, is converting the following decimal number to binary. What is the answer for 1011? Because this is a 2 power 0, 2 power 1, I will show you how to convert it into a decimal. Once again, decimal 4 is written, it is a 100. Do not read it as a 100. You always read it as a 0100. Whereas decimal 17, the answer is 10001. The next one is the binary to decimal conversion. Convert the binary to a decimal number. This is a simple example. So, you take the binary number and corresponding weights of that is according to the position value. This is a 2 power 0, whereas the next one is a 2 power 1. We call as LSB, whereas the extreme left side bit is called as the most significant bit. So, 2 power 1, 2 power 2. You are multiplying every binary bit by its corresponding weight, and finally, you are adding all these numbers. Therefore, when you add, the value of it is 51, right. So, therefore, the given binary is equal to how much it is in a decimal? It is equal to 51, right. The next one, the position value. So, based on the positional value, for example, as you know that there is a number, it is like a 444. How do you say it is a 444 in a decimal? The corresponding weight is 10 power 0 here, 10 power 1 and 10 power 2. That is what we are saying simply. It is the hundreds place, the next one is the tens place, whereas this is a units place. Therefore, when you multiply 4 with 100, 10 square is 100 plus then 4 into 10, then it is a 4 into 1. 10 power 0 is 1. 400 plus 40 plus 4. So, that finally the value becomes 444. So, that is what is called a position value or the place value, right. So, for example, it is a 1100. So, the corresponding weight for this is a 2 power 0 is multiplied with a 0 is 0. 2 power 1 is multiplied with a 0, it is a 0, whereas a 2 power 2 is multiplied with 1, therefore it is a 4. And this last MSB position weight is 2 cube multiplied with 1, it becomes a 8. So, finally, this is equal to 1100 is nothing like now, it is a 12 in a decimal number. Now, the small test is. So, what is the binary value of 1001 is equal to in a decimal number? So, the value is nothing like a number 9. How it is becomes the corresponding weight is 2 power 0, here it is a 2 power 8. So, 8 plus 1 is equal to 9, and in the binary 4 ones is equal to how much it is a 15, and the binary 10 is nothing like no, it is a 2, right. Next one is the 8421 code, which is also called as a BCD code. We always call it as a weighted code because we are writing any decimal number, whatever which is existed up to number 9 in a group of 4 binary bits. That is why it is called 8421 code. So, the 8 is nothing like no, here it is 2 cube and it is 2 square 2 power 1, and where it is equal to 2 power. So, according to the weights, this particular position weight is a 2 power 0 is 1, that is why it is called as a weighted code. So, you take a 24926, you are representing number 4 in a group of 4 binary bits, that is 0 1 0 0. Instead of writing 100, we are making use of 4 binary bits to represent the given decimal number in a group of 4 bits. Similarly, 9, whereas 2 I can write simply as a 10, but I am making use of another 2 more binary bits 0 0. That is how we are representing any decimal in a group of 4 bits. It is called a BCD code, or it is called as 8421 code. Convert the decimal number 350 to its BCD equivalent. We are writing 3 in a group of 4 bits, 5 as usually, and 0 we are writing with a 4 zeros. Next one is convert the following BCD code into its equivalent decimal, right. Now, the electronic translators, the whatever the conversions we just came to know that, which are called an encoder. We are converting a decimal number into a binary equivalent. Similarly, the binary equivalent into a decimal is done by a decoder electronic circuit. So, these two conversions are very important in any digital system, just like this particular calculator. This is a simple calculator. At the input, what we have is a decimal input, and at that output we have a binary output that is displayed on a display board, that is called simply LCD unit. So, for example, you take a number 0, how it is 0 is represented in terms of a 0 0 0, and you take another number here in a calculator numeric pad 101. Then next one is the number 7. The 7 is represented as a 111. This is how 3. The input decimal number in a calculator in the very beginning will be converted into its equivalent binary inside the circuit called an encoder, which is available in the integrated circuit form. This encoder translates simply the decimal into its equivalent binary, whereas at the end of this calculator, the next process is a decoding a binary to decimal. So, the binary input of, so you can look at the 0 is represented here as here in the 7 segmented display. What we have on the display unit of your 10 digit calculator or so, it is 7 segments. Next, if it is a 1, these 2 segments will glow, right, whereas for a 10, that is number 2, that these segments except these 2 segments of yellow in color will glow, whereas when you take the input of 1 1. What is 1 1? Is number 3. It is displayed like this. The next one is 1 0 0. 1 0 0 is number 4. So, this decoder translates a binary to decimal, whereas the decimals are shown on the 7 segment, and this decoder also drives the 7 segment display. Hexadecimal, the last number 2 systems are. Use 16 symbols. The base is 16 because we are using the 10 decimal numbers as well as the first 6 alphabets. Here the decimal numbers and its equivalent numbers are specified, and the corresponding hexadecimal numbers are 1, and for 9 it is a 9, whereas for 10 it is A, whereas for 15 we are representing with an F. Hexadecimal to this binary conversions are: C is represented with 4 binary bits and 3 with 4 binary bits, binary to hexadecimal conversion and hexadecimal to binary conversions. And decimal to hexadecimal conversions is we are dividing with a number 16 continuously, as you know that a decimal is converted into binary where we are divided with a number 2. So, we are writing the remainder separately, whereas this 15 is represented with a F, right. So, similarly hexadecimal to decimal conversion is the 2 dB is written as the corresponding weight of 16 power 0, 1 and 16 square. So, multiply and write them, then add. So, the final result is 731. Fine. Simple test is convert hexadecimal to binary. A6 is equal to how much it is. So, we are writing in terms of a 4 group of binary bits, and convert hexadecimal to this, convert the decimal to hexadecimal. Fine. Similarly, octal numbers. So, where we have a base is 8, we use up to 7 decimal numbers, 0 starting. A decimal number and its equivalent binary, then finally the octal numbers are written. See, for a note 8 is nothing like it is a 1 0, not like a 8 here, whereas 9 is this one 1 0 0 1, it is represented in a group of 3 binary bits, we are representing any binary. And finally, the octal to decimal conversion, it is same as that of your hexadecimal to decimal, of course binary to decimal conversion, right, that is 123. All these we can also get practice with the help of a scientific calculator, in which you can change to the different modes and we can simply check it out. Even the gates also we can verify, okay, and the study material of the textbooks, whereas the learning is one, and for a calculator you can make use of a emulator. Thank you. All the best. For any clarification you can contact me in the very first slide of my emails. Thank you so much.